Welcome everybody to the San Francisco Regional Mensa monthly gathering. We're very happy to have Dr. Tohidi talk to us today. So let me give a little introduction. Dr. Ali Tohidi is a fire and fluid dynamicist. His research and development interests are at the nexus of experimental, data-driven, and mathematical modeling of large-scale complex systems, particularly the phenomena revolving around fluid and fire. He received his MSc from Sharif University of Technology, where he showed the effects of wind-induced surface cooling on transport processes in aquatic canopies. He received his PhD in Civil and Environmental Engineering from Clemson University, where he studied wildfire spread via firebrand shower phenomenon. Later, he held a postdoctoral scholar position in the Fire Protection Engineering Department at the University of Maryland, College Park, where he worked on the combustion-induced thermomechanical failure of cellular solids, as well as dynamics of fire whirls and extreme fire behavior. His current efforts are focused on understanding the physics of wildfire spread across different scales and developing new models to better characterize the risk throughout the landscape. We welcome Dr. Tohidi to the talk today.
Thank you so much for this very nice introduction. I'm really pleased to be here and have the opportunity to share some of the research that I've done with the help of my colleagues and present it to this chapter of Mensa. Okay, can you see my screen? Okay, sounds good. And as for the Zoom goes, when I share my screen, I don't really get to see everyone. So if you had a question, just please either speak up or let our host knows so we can we don't miss on anyone. Okay, as you all know, this talk is going to be about the physics of wildfires, their spread mechanism, and some of the extreme cases that we see in the landscape. I'm an assistant professor of mechanical engineering in San Jose State University, and I'm also part of the Wildfire Interdisciplinary Research Center that is recently developed in San Jose State, so we can study wildfires from different aspects of this phenomenon. So before we start talking about wildfires, I think it is useful to take a moment and acknowledge why they became a problem for us, because if you talk to fire ecologists, most of them agree on this fact that wildfires are actually a natural way for forests to keep hygiene of the forest environment, burn all the dead fuels and really preserve the ecosystem of the forests. Wildfires become really problematic for us first when they happen to occur at the proximity of where we live, and when their intensity, severity, and frequency increases a lot. And this is the trend that we have been seeing so far in the past decades, that we see more frequent, more severe wildfires that are happening, especially in areas around us in California. And there's a lot of factors that are contributing to this. One of them is obviously climate change, and because of the detrimental effects that the climate change has, we are experiencing on average higher temperatures, which leads to more prolonged droughts, lower temperatures, lower moisture contents for the fields. And that basically lays the foundation for a high-risk area. So you just need an ignition source, either anthropogenic, human-caused, or lightning to have a fire. Also, as other part of the problem that we are having is our land development trends in areas that we call them wildland urban interface, or WUI. I don't know if you can see this pointer. This is basically the fact that over the past decades, we have developed a lot of communities in the areas that have either direct or somehow indirect interface with the wildland. And whenever a wildfire happens in the wildland and we are in the contact with it, we're obviously going to be affected. Another part of the problem is something that we call it oversuppression, and that has to do with the limited resources that are available to us. In a way that instead of spending the budget and money that we have to basically spend all that money on suppression effects, because the large area of fires that we have usually they require a lot of resources, a lot of air tankers, bulldozers, numerous and a lot of firefighters that need to manage these wildfires and contain them. So most of the money is being spent on that part, and we don't really get to do a lot of fuel management and land management in order to reduce the risk. And when we don't do that, we are effectively accumulating a lot of dead fuels at the lower levels of the canopy at the forests, and that is basically increasing the amount of risk, which is going to be combined with the effect of climate change, and we experience these effects. So if someone asks that wildfires are basically caused by climate change, now we need to basically mention all these problems that are confluencing together to cause these effects. And in terms of the impacts, I guess we are all living in California. We are experiencing the impacts actually right now. I don't really need to emphasize on how wildfires are impacting us. They burn millions of acres of land each year. We lose a lot of structures, infrastructures, and unfortunately, a lot of people because of them. Only in the past 2 years, the number of losses that we have had in terms of fatalities have surpassed 100. And in terms of the economic cost, the order of the economic cost is of the order of billions of dollars. And we are yet to see what has been the total cost that we've been experiencing in 2020, because we are in the middle of the wildfire season. Before I get into details of the work today, I guess this slide, which I have excerpted from one of the studies by Higuera, is a very important one to acknowledge that wildfires are a very complex, multi-scale and multi-physics problem. At the very small scales where you have combustion reaction going on, you have the effect of fuels, heat, and oxygen. This is basically the conventional fire triangle that you see and you're familiar with. And the spatial length scale there is of the order of, millimeter, micrometer, and the time scale is of the order of seconds. And that can basically affect a larger scale for wildland fires. And if you want to, if you want to talk about wildfires and their fire behavior, the influential factors becomes again fuel. Now, instead of the oxygen, the weather that we are dealing with, and also the topography of the region that these wildfires happen. On the grander scheme, when you want to talk about the trends of the wildfires, then you need to talk about the vegetation, as well as the climate of that region and the sources of ignition that we are dealing with. So we are able to characterize the fire regime in that region of the interest. So most of the work that I have been doing has been effectively around these two parts. And it is worth mentioning that each of these scales are basically feeding each other and creating a feedback to the next scale as these processes happen.
So, Dr. Tohidi, a couple people have asked for you to get maybe a little bit closer to the mic or speak up. It's a little bit
sure
quiet.
Is it better now?
Say something again.
Is it better now?
Yeah. Yeah, I think that's a bit better. Yep.
Okay, great.
We had one question come in, says, do we know why there's such a discrepancy between the impact of wildfires in 2018 and 2019? Or is there an estimate for this year?
I haven't seen an estimate for basically this year yet, because as I mentioned, we are still experiencing the wildfire season. But the discrepancy between 2018 and 2019 is that in 2018 we had the campfire and basically loss of a town, Paradise completely. We lost that town, and most of the incurred losses are basically related to that event. Fortunately, so far we haven't had anything close to that, and that's a really good thing. But 2018 was like an outlier in terms of the human losses that we've had, and hopefully it will never happen again. So that's one explanation that I can make for that. Okay, if we want to talk about wildfire spread mechanisms, I think most of you are familiar with these two main mechanisms. One of them is flame impingement on fuels, which we call it convection. And the other one is radiation, where electromagnetic waves that comes from the flame basically hit the material and increase the thermal content of the material. And if that increase in thermal energy or internal energy increases or passes the threshold, you effectively would have a ignition occurring. And these two mechanisms are documented very well in the literature, in the scientific literature. And there are still challenges with regard to scaling the understanding that we have at the laboratory scale to wildfire scale and also regional scale, as I mentioned. But in terms of the small scale studies, I think we have a good understanding of what are the effective processes there. But there's a third mechanisms by which wildfires propagate through our environment, and that's what we call it a firebrand shower. And this process happens when you have burning vegetation or structural elements that are burning, and due to combustion reactions, the material loses its structural integrity, and at some point it breaks off from the main structure and starts to basically get lofted through the fire plume and goes high up in the atmosphere. And as these particles go up in the atmosphere, they can be transported by wind in the downwind direction and land somewhere else far ahead of the fire front. And if they're still hot enough, they can ignite another fire, which we call them spot fires. And this can happen very close to the fire, main fire event, that you have direct impact of these, or far ahead of the fire front. These particles can basically accumulate, smolder for a while, and cause ignition. This is a process that is estimated to have responsibility for most of the losses that we are experiencing in wild and urban interface areas in terms of losses that we have for houses, the number of houses that are getting burned. So this video, I guess, shows this effect really well. This is a video from a fire in Australia, New South Wales, Australia. The camera that is mounted on an airplane is going around the fire, and it's an IR camera. So if you see these, can you see these glowing particles that are coming off of the fire? These are basically the firebrands, or the particles that we call them firebrands, that get lofted through the fire plume, as I mentioned, land fire off the fire front, and ignite another fire. And this area is basically between these two fronts is effectively intact and depending on the wind direction, fire can engage in that as well. So most of the research that I've done so far has been related to the phenomenon that I just showed you, and we call it firebrand shower. I've done studies on understanding the generation mechanisms, small scales, studies on thermal rolling effect, how these particles get lofted from the main structure. I've also studied some parts of the wildfires that has to do with the dynamics of the plume, which is something that I'm going to present today. Also, I have studied on the transport processes of these particles, where they go, how we can model them, and also some studies on the extreme wildfire behavior, one of the extreme cases, which we call it fire drill, or as is known, fire tornado. Also, during my work in a couple of startups, I have also worked on data-driven methods to characterize wildfire spread through the landscape on larger scales, because on the operational side, we are still struggling with predicting some parts or some types of the fires. And I believe these type of methods can really help us in understanding how we can improve the rate of spread models. So in terms of the near field plume dynamic study that we've done, if you look at the plume from a wildfire that you can see on the bottom left, it has some similarities with the smokestack plume. Also, the plume that comes off of the fires that burn due to oil spill, and also volcanic eruptions. These are all highly buoyant plumes. And the characteristic of these plumes is that because they are buoyant, and the origin of these plumes comes from a source with a very high temperature, they have a high buoyancy flux. And that causes some important changes in their trajectory compared to these smokestack plumes, where usually the buoyancy is lower. And the motivation of this study was to understand how we can model wildfires better, because before we do this study, if you look at the literature that we had, most of the studies that were looking at the problem were considering the wind as a uniform boundary layer, and weren't really considering the effect of the canopies, interactions with the topography and so on, that causes the shearing effects in the boundary layer. So we wanted to kind of characterize what are the best conditions under which we can study wildfires. And to do that, we created a mathematical model for these plumes. This image here shows you the plume envelope. This is the plume envelope extent, and this is the cross section that we are considering for the plume, which is an ellipsoid. And if you write down the plume equations based on the characteristic fluxes that you see there, which are effectively the plume discharge, the volume of the smoke that you have per second, also the momentum that's get transferred from the fire to the plume, which is the velocity times the volume rate of the plume, and also the buoyancy term, which we show it by F. And that has to do with the differences in the density of the plume with respect to the environment. You can really simplify these Navier-Stokes equations that we deal with to solve for the trajectory of the plumes, which we show it here by the dashed line, and really predict the trajectory. This is very important for us, because if you can predict the trajectory, you can have a really good estimate of the plume envelope, as well as knowing what would be the extent of the wildfire plume impact on the communities. And you can really understand the extent of the emissions that the fire is releasing. So we, using that model, or those equations, we developed a numerical model that we could solve for a variety of different parameters that affect the plume dynamics. And the final result that we get, and I'm presenting it in this slide, is that wildfire plumes are different from smokestack plumes, that we can't really consider a uniform boundary layer for modeling them. We need to really account for the shearing effects, as well as canopies, the topography, to model the trajectory. On the far left top, you see the centerline trajectory of the plume from a smokestack that is released through the boundary layer. This is basically the wind velocity profile. And there is really no difference between whether you release it through a uniform boundary layer or a non-uniform boundary layer. And by non-uniform, I mean this logarithmic velocity distribution. But if you look at the case of wildfires, using that numerical model, we showed that if you release it through a uniform boundary layer, the velocity is good, the centerline trajectory is going to be really steep. Whereas what it's happening in reality, which is shown by red here, is that the plume bends much faster. And that has really significant consequences for us, because it directly affects where these particles that we talked about, and we call them firebrands, can go, and how high they can travel through the atmosphere, and what will be the maximum landing location of them. So that was basically the main result of this study. And once we knew it, we wanted to create conditions, controlled conditions under which we can study them better. This is another slide that shows the difference between the wildfire plumes from smokestack or industrial plumes that we could measure their initial conditions on, and you can see a drastic difference between the wildfire plumes and the rest of the data that you get from different types of the plumes on the scale of different parameters that these type of plumes have. So there's a clear distinction between them. Once we knew that we needed to model the entire boundary layer to understand the plume extent, we decided to model the firebrand shower behavior, or what you saw experimentally in a wind tunnel. So this is a wind tunnel in Clemson University, which is a mid-sized wind tunnel. The cross section, I believe it's 3 meters, and the length of the test section is 5 meters. And we have these spiral elements and surface roughness elements to basically create that curve in the velocity distribution of the boundary layer that we can get from these fans that are blowing through the wind tunnel. And we also had a jet built underneath the wind tunnel with just 2 blowers that we could buy from Amazon to create the smoke behavior that we get from the wildfires in the lab. So effectively, we had wind that is coming from the wind tunnel, these fans, and develops over the test session, and also the jet that kind of tries to mimic the behavior of the fire plume. And we could run these for different, speeds or fan speeds to create different interactions between them. And once you let the system to run for a while, we started to release these, tiny particles which are made from polyurethane in the exit nozzle of this jet and try to measure their trajectory, see where they land. And by doing this, we wanted to experimentally model the firebrand shower behavior, release of those particles that I showed you in the movie. If you start to film, these experiments from the side view, which is what we did, you can start to develop, computer vision algorithms in order to track their trajectory. In this slide, what you can see is basically the original frame of the camera that I showed you, and this is the particle, the red dot here. And then you go through some operations, which are very simple operations, and you can really see how they basically fly through the velocity field that is created similar to what we see in reality. Obviously, it's a much scaled down version of that velocity, but here on the right to left, it's the wind from the wind tunnel, and here is the jet, where you have this updraft velocity where we release these particles that are coming off. So if you do this for all these particles and measure their trajectory using this computer vision algorithm that we developed, and kind of show all the trajectories that are resolved on the same plot, it looks something like this. And again, this is the jet nozzle. This is basically the trajectory of all these particles. It is very difficult to make a really solid conclusion from the behavior of these particles. As you can see, there's a lot of stochasticity with the landing distribution of them, although all these particles are released within a similar velocity field, so there's not a lot of change in the velocity field, and the size and aspect ratio of them are the same. So what is causing this variation in the landing location, which is very important for us? It has to do with the aerodynamics of these particles and the motion that they experience as they land. So what we can do to effectively describe their behavior is to plot the kernel PDF of the landing location. And if we do that, you see the kernel PDF of the landing location for different aspect ratio of these particles that I just showed you is very similar to each other. So effectively, their mean is very similar. And we did that for all the experiments that we've done. So in these plots from left to right, the jet velocity increases, and from top to bottom, the boundary layer or wind tunnel speed increases. And as the velocity increases, you expect these particles to land further. And the mean of these PDFs basically move further and increases. And this is the behavior that we see in the experiments, which wasn't really characterized in the previous studies experimentally. We also characterize these parameter, space of these experiments in a way that we could explain by increasing the aerodynamic force on these tiny particles. You see that they land in farther distances from the jet, but if you increase the jet velocity, which kind of mimics the fire output of the fire, or exit velocity of the jet there, you can't really predict the behavior there. So what we try to do is to numerically model this behavior. So here you see the computational domain that we have. This is basically the wind tunnel in Clemson University that we numerically modeled. This is the jet, and this is the test section of that experiments that we had. So effectively, we are releasing the particles from this so we can see where they land. This slide shows the resolved velocity field that we could create using computational fluid dynamics methods. And what you see is the kinematic viscosity for the jet that is released from here. And this is the boundary layer. Then we use this velocity field to couple it with particle trajectory or transport model, which is a fully deterministic, three-dimensional and 6 degrees of freedom solver that we use in order to really understand where these particles go. And if you do that and solve these system of equations on top, this is one of the experiments that we just see. So these are the trajectories that we resolved from the experiments, wind tunnel experiments that we did. And on the bottom, this is the simulation that we made for the exact same experiment. So as you see, there's a lot of similarity between the numerical model that we created and also what we ended up measuring in the experiments. And the motivation of this part is that we really need to understand where these particles go in order to have a better estimate of the total losses that we would have for the given fire. And recently we have started to work on a new type of model that we can integrate it with operational models such that whoever is using these models is capable of characterizing the risk from wildfires due to firebrand shower. And although the fire fund is not really there, they can have a better estimate of what will be the estimated risk of ignition due to this process. Is there any question so far?
No.
Okay. So I guess we can move to the other parts.
Well,
as
actually,
I mentioned, this is an ongoing study that we want to extend it to larger.
Actually, there was one question that came in. Can I read that one?
Yeah, absolutely.
Yeah. So a garden hose with plenty of well pump pressure was sufficient last year to allow some Sonoma County homeowners to save their properties from wind-borne falling firebrands, where during some gusts the hose could barely keep up and the main fire was reported to be miles away. But after a couple of hours, once the roof and yard plants were soaked, the firebrands simply sizzled out in wet grass. The result after a couple of days was heat-discolored roofing and charred spots in the grass. The trees were soaked too, and none were flared up. These people saved their group of homes while subdivisions near around burned to the ground. Passing police allowed them to stay since they were actively fighting fire spread. So I guess this is kind of a question and a comment about people doing things to like soak roofs and what would be the effect of the firebrands on like home defense sort of activities.
Yeah. So if you look at the guidelines that we have for home defense against wildfires, a lot of times you hear a term called defensible space, right? And the defensible space is usually related to the first two mechanisms that we had for convection and radiation, and doesn't really work for basically the effect of firebrand showers that we might get. In my view, whatever measure that we can take in order to reduce the heat transfer from these firebrands that can accumulate over the roofs, over the porch area or any area that can cause ignition in your proximity is an effective measure, in a way that by basically doing that, you're reducing the risk of ignition and the possibility of ignition. A lot of times, people talk about these pumps and, these walls of moist air that they can create around the houses. But I am not aware of any specific study or a systematic study to measure their effectiveness in a meaningful way. So if you know any study that has measured the effectiveness of them, please let me know and send it to me, because that's a really important uh, measure that we can take. But as I mentioned, any measure that you can take to reduce the heat transfer from these particles to the bed, which can be the house, the ceiling, porch, it should be a good measure.
Great, thank you.
Mm-hmm. I hope that answers the question. So now that we talked about the firebrand shower problem, I want to take this and basically use this opportunity to talk about the fire wheels, which is one of the extreme behaviors that we see during wildfires, and I have done some theoretical studies about it. As you can see, this is a example of the fire wheels, which is this very prolonged flame or a column that occurs either in wildfires, the structural burns that we have. And why we need to study this phenomenon is due to the fact that when such a phenomenon happens, usually it is associated with intense heat, and it causes a lot of brands or embers, or as we call them, firebrands, to basically dissipated from the main source. And a lot of times when they happen in wildland fires, their occurrence is very abrupt, and you can't really predict when you're going to have a fire drill. And that can pose some dangers to firefighters and first responders. So we are very interested in studying them to better characterize their behavior and mitigate the effects. Also, in some cases, they can be beneficial if we use them in the right setting. So this is a picture of a very small scale fire drill, which is called Blue Reel, that the colleagues who helped me to basically put together this review study created in their lab, and it is shown that it has a higher combustion efficiency. Also, it is good to know that the flames like this happen over centimeters, but fire wheels can have a lot of different scales, spatial scales. This is something that you can create in a lab under controlled laboratory conditions. You can see different fire wheels in Burning Man in this image, and also over a discrete array of the flames that you can create. And the point here is that these things can happen over a wide range of scales. If you look at their history, they come with a lot of different names. Fire tornado, fire devil, fire NATO, dragon twist, and sometimes these names have a very specific definition. But for the sake of simplicity, we call them fire wheels. On the right, you see a painting from the Great Kanto earthquake, which happened in Japan in 1923. And after that, they had a very large urban conflagration that led to a large fire wheel, and they had a lot of fatalities. So this is one of the recorded documents that we have for that event. Also, we've had events in Canberra, Australia, Christchurch, New Zealand, and Car Fire, which I'm going to show some of the videos related to that. But if you look at the scientific literature, there are two main studies that we can mention, done by Ram on the left and Emmons on the right, which they created fire wheels in laboratory setting by a fixed frame and also a rotating mesh. So effectively, you can create fire wheels by having a rotating mesh around the source of the fire, and we'll get to see why that is effective in creating that. But here I want to show you this video from the Canberra, Australia fire, and emphasize on the fact that you would have wildfires, during wildfires, a fire will to happen under these three conditions. Whenever you have a thermally driven fluid sink or fire or a fire source, and a mechanism to effectively create these you know, the rotational effects or vorticity generation mechanism in a way that it can you know, shed eddies into your environment. And also you have a you know, friction at the bottom such that you can create like a boundary layer that feeds to the fire flame. You would have these type of structures in the flame to be created. So these are the three essential conditions for having a fire wheel, and when they coincide, you can expect a fire wheel to basically happen. You know, on the science part, there are a lot of, you know, different factors in you know, creating each of these effects. We can summarize them by talking about the vorticity ring that goes up due to the fire heat, and due to some you know, rotational or eddies that are available in your domain. This vorticity ring can tilt, get stretched, and eventually converts to a column of the flame. And the reason for that is, you know, as these flames are you know, tilting and stretching, the access of the flame to the oxygen reduces, and the flame needs to basically elongate for more access to the oxygen to continue the the burning process. And that's one of the main reasons that you see these very long flames in these phenomena. This is a video that shows you the pronounced effect of the fluid sink, as well as the boundary layer. You know, basically these structures that you see on the ground, and as I mentioned, these structures can carry a lot of, you know, brands and particles within them, and cause problems. This is a burn experiment, so the particles that are being transported, I'm not sure about they are vegetation, so it's fine, but in the next videos we'll see some more effect of it. This is a video which is from car fire that happened in 2018, I believe, in California, and shows the very large scale of these you know, fire wheels that happen. And you know, atmospheric scientists, they call it fire tornado, you know, if I'm not mistaken. But looking at the scale of this fire, due to immense heat that is generating and the interaction that is having with the boundary layer, effectively you are having a fire weather event here. That's the fire has created its own weather, and it can be very destructive. So from all these examples that we have seen, we can effectively characterize or categorize these type of fires to three main categories. The first category are the ones that basically stay on the source and burn with a little fluctuation, you know, around them, but not a lot, which is basically shown here. The second type are the ones that form over a line of fire and can, you know, go back and forth along this line, as you can see in this image. And the third type is the ones that can create over the source, can be created over the source and from an L-shape type of fire, and can bring the flame within themselves into this region. As I mentioned, whenever you have situations where you have this intense heat combined with a source of rotation in your system, as well as a boundary layer that can basically force air into the fire, you can basically see these structures in your environment. And these are different type of scenarios that kind of satisfies these three requirements that I just mentioned. This is an event that is very interesting. It actually shows one of the types that we just discussed. So the fire is happening here near the river, and as you can see, it can create this vertical structure, and at some point you're seeing the water is basically getting engaged here, and it becomes like a fire over water. So if you look at what is dropping on the river, yeah, these are the particles that I showed you, that these structures can get and basically drop far away from the fire itself. So in the terminology, we call these types of rotating plumes that occur near the fire, the L-shaped area. We also call these fire wheels and categorize them as fire wheels, but I know these are called fire spouts as well. Also, the last slide, I want to mention that these type of structures are not like in a single one that can happen. If you look at this IR image that is taken from a fire, multiple of them can happen at the same time. You can see one here, another one here, and they can quickly travel through the domain. So it is very important to be aware of their occurrence and stay away from them, especially for the first responders and firefighters, because they can experience severe burns. So with that, just wanted to thank you for this opportunity and taking all questions.
No, thank you very much. Yeah, we had a couple of questions in the chat. The most recent one is straightforward. This is from Michael. I had never seen a fire whirl until the fire tornado in Paradise. Are they common or just not mentioned often?
These are basically as I mentioned, whenever you have those three factors in your fire, where you have a source of fire that is creating an intense heat. Also, you have a system or a mechanism that can create rotation in the environment. And as long as you are basically having these accompanied with a ground that can create a radial boundary layer, or have some friction between the air that is going through the fire, you can see them. In terms of larger scale, fire wheels or fire tornado, I don't know how common they are, but we are starting to see, more of them. And, one factor of that can be due to this reality that, everyone now these days have like a, smartphone that they can start, take a video from them, compared to the past that we just get a painting or some description from these type of fires. But as the severity of the wildfires starts to increase, and we see more of them throughout different landscapes, I believe their probability of happening also increases as well.
Okay, great. We had another question from Susan. Is your research thus far descriptive, or has it led to practical application, as in something that would not have otherwise occurred, or your research has, you know, changed or influenced how people read fires or that sort of thing?
That's a difficult question to have answered, but you know, we hope to basically convert part of these studies that we've made and translate them to either codes and standards or the operational models that people use, yeah, especially first responders. But the difference between fires and other hazards is that it is so dynamic, and a lot of different parameters are playing a role in them. So you can't really generalize the behavior and have like a tool that they use and come up with solutions. So that's one aspect of it. The other thing is that we are just starting to basically understand the fundamental mechanisms of these type of flames, and it takes you know, some time for us to have a very solid understanding and then come up with solutions that can people really apply and convert this to applied basically knowledge. So far it's been mostly experimental work and scale analysis with regard to firewalls. For firebrands, we have a better understanding in terms of the transport, where they can land, but on the generation of these particles, as well as their ignition upon landing, we still have a lot of studies to basically do and characterize the behavior.
Great, thank you. So we had another question come in. World War II bombing in Europe produced firestorms like these fire columns. Are there studies of those, or how fire spread during those attacks?
Yes, I've heard about them, especially Dresden in Germany. These are real cases that have been reported. I'm not aware of the study that specifically studies these events and characterize them in a meaningful way in terms of, you know, measuring, you know, power output or, you know, things that are important at the source. But I know some researchers in Miso Lofire lab are starting that process to study them. And the main reason for that is there's a lot of similarity between these type of events and another, you know, extreme fire behavior that we see and we didn't mention here, that can effectively create its own fire weather and be very destructive.
Great. We don't have any other questions in the chat. We have like about 3 more minutes. If anybody wants to speak up and ask any questions, we welcome anybody to unmute and do so.
Are any of these studies occurring in full-size labs? I saw an example of a fire tornado there in the model in the lab. Are there any full-size studies going on where they converted an entire pasture or something like that and produce such firestorms at the, you know, 100 and 200 feet level?
No, I don't think so. You know, we are very limited on, you know, generating very large fires in the labs, because as it gets larger, the power output of the fire also increases, and you have to deal with a lot of, you know, radiation, and that effectively melts a lot of the instrumentation around it. So I think most of the studies that have done that are done so far are kept at the, you know, the very small scale, you know, at most couple meters long, you know, in terms of the flame length. but not to that level. I'm not aware. Maybe in very large scale labs that's possible, but I can see there would be a lot of challenges in creating that fire first, and then having meaningful measurements around it, because it becomes very challenging.
Another question in the chat: do you go out to fire scenes to watch?
No, unfortunately, I haven't been to a real fire. Obviously, if you want to be there, you have to be red carded and have some permissions. But I'm planning to get red carded soon, and hopefully I can be to a real fire. But in the center that we have, Dr. Greg Clements, they have radar trucks, and they have the permissions to basically get close to the wildfires. They use the radar technology to characterize the plume of the fire and measure its behavior. I'm not aware of any other group that can do that. Basically, they literally chase fires with their trucks. Yeah. So
we have time for one more question. So we had a great question from Leona come in. How far back does the study of fires go? Decades, centuries? Are there patterns on the globe where a majority of fires tend to occur? And if so, do we know why? Or are certain areas of the globe fire-free? Or do you think the entire planet has had fires?
And by fire, I want to be more specific. We are talking about wildfires, right? Because fire can be a structural fire, you can have different types of flames and so forth. But in terms of the wildfires, whenever you have those three factors in the fire triangle, fuel, oxygen, and a source of ignition, a fire can happen. But depending on the patterns of that region, these can grow to very large, wildfires, or can be basically smaller for a while, and then nothing really happens. So I would say the fire is a very, ubiquitous problem throughout the globe. We have fires not only in the US, in parts of Siberia, when the temperature is basically very low. We have fires in the Middle East. We have fires in Africa, Australia, and recently we have seen fires in China as well. So it's a global problem, but in terms of the patterns, since it depends on the weather patterns, vegetation, we can't really generalize them. And we need to really study each region by its own characteristics.
And the other part of that question is, how far back does the study of fires go? Do you see civilizations like 1,000 years ago planning to live with wildfires or not? Like, do you know the history of it?
Yeah, I know in Middle East and also in America, indigenous people, they have been using fire as a tool to basically maintain the land and keep the hygiene of the land in a way that burning dead fuels and kind of help the forest to regrow. And this has been a really effective practice for them for thousands of years, and they have been doing it. I believe there's a group, it should be either in California or Oregon, I'm not sure. There's an indigenous group that they've started to be active in basically using fire as a tool for land management. And if you talk to fire ecologists, a lot of them believe in the effectiveness of fire in land management, fuel management, so we don't really end up with such a high risk environment.
Well, great. We're just a couple of minutes over. I want to have everybody thank. You can maybe unmute and say thank you to Dr. Tohidi for the great talk today. We really, really appreciated it. And yeah, so we thank you so much for joining our talk today.
Thanks a lot. Really appreciate having you here. And it was really nice seeing everyone.